Hello guys, welcome to episode 7 of HaskellRank series where we solve programming problems using Haskell. So for today's episode, I have basically two things that I want to focus on. First thing is we're going to introduce and make use of modules in Haskell. Modules are essentially very similar to the whole idea of packages, or I mean, you typically use modules in almost every programming language. The idea is, of course, that you would be able to segregate and keep, sort of build abstractions in separate modules, and that way you'd be able to sort of, build better design, and you can. Also manage slightly bigger code bases much more easily because you keep them in separate modules, and yeah, we're going to make use of that. And the second thing, which I'll get right into right now, is introducing something pretty awesome which exists for Haskell documentation lookup. So now there's a tool called Hoogle. Let's look at what this is. Like the name suggests, because it's a play on the word Google, like it suggests, it is of course a service which you can use for searching through Haskell packages for documentation for on functionality that exists. However, there is something very unique to Google, which is that you can actually not only look up functions by searching for keywords, which is what you probably do for any other tool, for any other language as well. But here, because we're dealing with Haskell, you have the ability to also do lookups based on the type signatures of function, and that I believe is a pretty awesome and amazing thing. As an example, let's quickly see. I mean, there are examples given here itself. Like for instance, you can actually search for signature of the map function. This is an example where I'm actually looking up by the type signatures. The fact that we can search by type signatures just blows my mind. It is definitely by far the most one of the most amazing things that exists. I'm going to tackle yet another advent of code problem. This one is titled Jurassic Jigsaw, and I and this was by far the probably the most difficult problem that came out in advent of code 2020. Let's get right into it. So let's quickly go through the problem statement, right? So the high-speed train leaves the forest and quickly carries you south. You can even see a desert in the distance. Since you have some spare time, you might as well see if there was anything interesting in the image the Mythical Information Bureau satellite captured. After decoding the satellite messages, you discover that the data actually contains many small images created by the satellite's camera array. The camera array consists of many cameras. Rather than produce a single square image, they produce many smaller square image tiles that need to be reassembled back into a single image. Now each camera in the camera array returns a single monochrome image tile with a random unique ID number. The tiles, your puzzle input, arrived in a random order. Okay. Worst yet, the camera array appears to be malfunctioning. Each image tile has been rotated and flipped to a random orientation. This is the key here, which made the problem fairly difficult. So your first task is to reassemble the original image by orienting the tiles so that they fit together. To show that the tiles should be reassembled, each tile's image data includes a border that should line up exactly with its adjacent tiles. All the tiles have this border, and that border lines up exactly when the tiles are both oriented correctly. The tiles at the edge of the image also have this border, but the outermost edges won't line up with any other tiles. Right. For example, suppose you have the following 9 tiles. So this is a sample test kit that has been given. We'll be using this for testing our solution. Now by rotating, flipping and rearranging them, you can find a square arrangement that causes all adjacent borders to line up, and we finally get sort of an image. As you can see here, all the the overlapping, the common boundaries of the values between any two tiles would be exactly the same. So the pattern that you see here on the right edge of this tile would be exactly same as the left edge of this tile, and so on and so forth for all the tiles. So for tiles, whoever are sharing their borders must exactly match, right? So for reference, the IDs of the above tiles are so and so forth. Okay, and to check that you've assembled the image correctly, multiply the IDs of the 4 corner tiles together. If you do this with the assembled tiles from the example above, you get this big number. Now assemble the tiles into an image. What do you get if you multiply together the IDs of the 4 corner tiles? Now it suggests that the first thing that we need to do is sort of come up with the basically stitch the tiles together and come up with the final image, and from that they say, okay, we will utilize the corner tiles IDs to get this number. For the purpose of this specific answer that they need, we actually don't need to get the final image at all. All we really care about are what tiles are the corner tiles and what their IDs are. And as long as we can determine whether a specific tile is a corner tile, that's sufficient for us, right? We don't actually have to come up with the final image where we're able to match all the tiles, get their current orientations, and things like that. So that way we can avoid having to do a lot of complex computation, and we can just straight away look at the corner tiles. And as you can see, I mean, maybe perhaps looking at this smaller grid where we are actually just shown the tile IDs, it would become apparent to you that when you look at the corner tiles, they are unique in the sense that they share borders only with 2 other tiles. Right? However, if you look at, maybe let's say for example, the edge tiles, these tiles share border with 3 other tiles, and if you look at any inner tile, they will share border with 4 other tiles, right? So this helps us very uniquely cherry pick tiles with specific, and as far as corners are concerned, we know, right, they share borders with only 2 tiles. And no matter how big the size of the final image is, we will always have only 4 corners. So it boils down to just being able to determine okay, which tiles are adjacent to each other, and then from that we would maybe build some sort of an adjacency matrix, which gives us, okay, given a tile, it has so and so number of adjacent tiles, and then from that we can filter down and get only the tiles which have which are adjacent to only 2 others. So basically they'll be the corner tiles, and as long as we can do that, we'll be able to then very easily get this answer without having to actually worry about each individual tile's correct orientation and stuff like that. The only one minor catch is because it's stated that the tiles are randomly oriented. What we can do to work around that problem is simply that when we are comparing edges, we can compare whether the edges are themselves directly equal, or if not, we would look at we'll also be comparing the edge with the reverse of the other edge, right? So as long as it compares to either the edge or the reverse of the edge, we know that they are adjacent, and that way we can avoid having to again, we can avoid having to compute or derive what the current orientation is and whatnot. As long as it matches, we know that they are adjacent, and we can use that fairly easily to build our adjacency matrix. Okay, so let's start maybe solving the problem. Okay, so obviously the first step is in fact to try to basically parse our input, but for that purpose, what I'm going to do, since I said we'll be focusing on utilizing modules, so let's do one thing, like, because we are going to be dealing with tile data, let's create a separate module just to capture all the functionality that we'll need for this data, right? Which will include everything such as parsing the tiles, and then maybe the other minor computations that we need, things like, okay, determining whether two tiles are adjacent to each other or not, and the adjacency matrix also, right? Let's do that first. In Haskell, you can create modules just like any other programming language. The only requirement is the fact that the modules and the file names are case sensitive, in the sense that they should be capitalized, matching the cases, matching the exact case of the module name itself. That's the only minor piece. So we'll first let's start with the tile module. And so for the purpose of our problem today, what I'll do is we'll perhaps create a modules directory. Let's call it modules. Pretty unoriginal. So we'll call it modules, and then we'll create our first module, which will be the tile. Okay. And so how you create modules in Haskell is fairly simple. So you use the module keyword, and you give basically a name to your module. In this case, I'll say, okay, this is tile. Oh no, in fact, in this case, I will say it is modules.tile because it is namespace under the modules directory, right? Yes. And we'll simply say where, and we'll start our implementation. Now we can obviously cherry pick individual functions that we want to expose, and I think we'll get to that in a little bit. So first thing first, let's start with maybe looking at how to parse the tile data. Okay. In fact, even before parsing, let's try building the data structure for our tile. Right. So I think I'll go ahead and probably use define my tile type using the record syntax, again just to keep things slightly simple. And I think it works out also pretty well when it comes to, because as you remember from my last episode, the properties that you so in this case we have a TileID, right, which is an integer, and then we will, let's say, have pixels, which is basically which will basically capture the pixels of each individual tile, right? What we have here, the dots and hashes. Okay. And so we can use this. Because we know that these are individual functions which we can use for pattern matching and for extracting the information from our tile type. We can, since they are functions, we can actually even expose them to the outside world. And even right away, since we've created this type, we obviously want to expose this type, and that we can do with something like this. So we say the modules or tile exposes the tile type, where the tile where the dependencies are defined in so and so, right? And so this way we've now already exported our tile data type, by the way. Okay. I think the first thing I want to do is start with passing the tile ID. So for that, what basically we will take maybe the first line of the tile information as input, and we will try to parse the ID from it, which would be an integer. Okay. Okay, as you can see, what we can do here is we can split the thing by words, and we can pick the last value from words, right? So basically we'll split it into tile and then the ID with the colon. And so we can, when we say last of words, we will be getting basically the number with the colon, and so I want to get rid of the colon, and for that we can use the function init, right? So init is the function that basically it returns all the elements of a list except the last one. So basically we'll omit the colon, and then we'll get just 2311, the ID, and we can simply use read to parse this. So here we have a very nice point-free notation function where so now we first split by words, then get the last of it, then use init to extract only the numbers or digits. There are probably obviously other ways to do this, but I'm just doing it using a very simplistic approach. So this would be able to parse the ID from it. Okay, now let's try parsing an individual tile. So again, so here we will get a string, right? No, we will get a list of string. Sorry, we will get a list of strings, and we'll worry about how to get the list of string isolated just for the tile later. But let's assume we have that already, and so from a list of string, we should be able to pass that into a tile object. Let's see what this might look like. But the first thing we need to do, obviously, is take the first we'll try to extract the tile ID essentially, right? And so for that we can use our parse tile ID function and just basically get the head of our tile string, right? Let's call it this for now. So we can basically get the head, which gives us the first line, right? Yeah, the first line or the first string in the list of strings, right? So we get this, and we'll just call parse tile ID to get our ID. And the next thing we want is the pixels. Now pixels would be essentially all the remaining one, so we can just simply say tail of ts, believe so now that we have that, we can create a tile, which will be tile ID, and pixels will be pixels. We have it. Now we know how to parse the tile. Now let's try to come up with our implementation where, let's say we're given this entire input as a single string, and we should be able to convert that into a list of tiles. Now just following the pattern we use, for example, for functions such as words or lines, what I want to do is follow that similar naming pattern and maybe just call my function tiles, which would essentially get this entire thing input as one string, and then from that it will be able to generate and give me a list of tiles. That's what I want to do. And the reason I want to call it tiles and not maybe like parse tiles is just to sort of keep the naming sort of, in the same in line with the naming convention that we are already using for parsing input, using when we use functions like words or lists, right? Yeah, just for that reason, no other reason. So tiles again will receive the one giant string, which what we need to do for that is we need to be able to split that. First thing is split that into a list of list, right? A two-dimensional essentially, where each component of that list we could use parse tile to parse that individually, and then so from that we'll easily be able to finally get a list of tiles. That's what we want to do. Now in order for us to split the input, what ideally I want to do is utilize this very simple thing that we know, that basically there's an empty line space which separates each individual tile data, right? So we know, given that, we know that basically at the end of all the tile data we will have 1 and 2 new line characters. So we will essentially have 2 new line characters, and that is unique because obviously at the end of each line here we still have new line characters, but there will be only one there. However, here uniquely we know that there are 2 new line characters, and we can use this to sort of split our their input data into that. So now, given that we want to do this, let's see what options we have, and let's use Google for our let's use Google to try to search for some functionality that is applicable. So let's say we basically have a string, and we would need another string as input, which would be a delimiter, which would be basically the double new line characters for us, but we'll always see it will be a string, and eventually we should be able to return a list of strings, right? That's what we want. So let's see what Google says that this corresponds to. Now we could use tokenization that has a similar signature. And there's a bunch of other functionality that has very similar type signature. Most of these are for dealing with numbers, and we have some weird looking stuff. Since I already know, we can actually look at a function called split, and so this is available in a bunch of packages, but the one I think which is directly available to us without actually any third-party dependencies is the one inside the data.txt package, and I think we'll probably try to utilize that. And so if you look at the type signature for split on is exactly what we want, except instead of a string we deal with the text type. But what I can obviously do is we'll do qualified import, because I think there are a bunch of functions in the package which clash with names for functions in Prelude, things like words, lines, and stuff like that, because we have all these functions defined also for the text type. Now that we have this, we can then look up the documentation for split on. No, is there a typo? Oh no, it will be t.split on, sorry. Right, that's a bit big. We can break a text into pieces separated by the first text argument, which cannot be empty. So in our case, essentially it will be the double new line character that was talking about, right? Now, so since it's going to be a text, what I can do is have, okay, where TileID is oh, we have to first import. And so this is what we want to delimit by, right? And so I'm using here a function called pack, and what that does essentially takes a string and then wraps it and gives you a text type. Now basically just to go maybe a little bit into what text is and why it exists, I suppose, is the fact that I think text tries to be sort of a layer above string, as in because it has good support for a lot of different things, such as Unicode characters and other complex pieces. So they've captured all that in this package. That's what I understand. But now that we have the Delium, what we want to do is now we would have, yeah, we basically want to use the split function. We want to split using the tile delimiter, and we want to call this on let's say this is ts. Let's just think ts. Now if you say so this would give us basically a list of texts, right? It will be a list of text, not a list of strings. So what we can do is we can use map with this thing. We can map using unpack, t.unpack. Now this does the reverse, where it basically converts the text type back into string, right? So we get back a list of string, and we can use this with parse style essentially, right? And in fact we can really use this like this. If I can spell it right, Although this already looks somewhat right, but I see that there's a yes. So my TS is actually a string. So what we need to probably do is we'll pack it. This will give me a big text, right? If we pack it, now we get a text. And so we can then use the split on function. It says what? Oh no, wait. We have to use map again. And yeah, so we can do a reta reduction, which I'll probably do in the end. Let's do it. Right, we can remove this and then we can convert all the dollars to it should be good, right? What's the issue? It says why not? Okay. What else? No, it says good man. Yeah. Which split on gives it would give me split on will give me back a list of text. And since we are applying a map, basically we will then a list of text. Each individual text we have to do lines. No. Something like this? Yeah. Because split on will basically give us the list of text, right? Where each text is essentially the entire text for one individual tile. So we use the unpack to extract the string out of the text to get back the string. Then we can split them by lines, right? Because we can split them by lines, and that way we'll get the list of all the lines for the tile, and we can then simply use pass tile to finally pass it into a tile. This works. So this way now we are already able to parse it. Now this obviously definitely is one function that I want to export. What did I do? Right, and so let's say tiles. Let's use this. Okay, this probably looks better. We'll export this. We don't really need to export pass tile or pass tile ID because I don't really see the need to do this individually. We'll just be able to use our thing to pass the entire input, right? So for instance, when we look at now let's look at what this looks like. Okay, so this is our boilerplate for the main and so now instead of doing any words or thing, what we will do is we will use a tile function. Of course we would have to import a tile function, and for that we will first import a tile module. Okay, now this says full match tile. It just says that this gives us a list of tiles, right? And for right now let's just do this way. Right? Let's just see what this looks like. So now I'm trying to run this against the test input. As you can see, we've been able to successfully pass the tile ID, and we have the pixel data as well for that tile, and we've been able to so this is one tile, and then we have a list of tiles, so we've been able to successfully pass them, which is awesome. And we've been able to nicely wrap all of this functionality into this module, hiding all the unnecessary details. From the outside world, all we care about is how to pass the tiles, at least for the time being, right? I think that's neat. That's essentially the main use case for modules in any programming language. That's the basic main use case. You want to be able to build abstractions basically, right, in a neat fashion. Okay. What is the next thing we want? Next thing I think we want to probably get into is towards let's probably first get into building a logic to determine whether two given tiles are adjacent to each other. I think let's do that first. And because if we know that given any two tiles are adjacent to each other, either they are or they're not, right? So it's just a boolean. So as long as we know if two given tiles are adjacent to each other, we can use that to then finally build our adjacency matrix, where we know for each given tile how many neighbors it has, right? Or how many adjacent tiles it has. Let's use is neighbor. Let's use this as our naming. So we will basically take two tiles as input and then eventually respond with a boolean indicating whether these tiles are neighbors or not. Let's do that. And so this first one is okay. Let's just think about what we want to do for this. Now obviously what we need to do is compare the edges, and like I said, what we can do is we can compare either the edges themselves or compare it with the reverse of those, but we definitely want the edges of the tiles and then compare them. So let's do that first then. Let's try to get the edges then. Okay, let's look at them individually then. So we obviously have four edges, right? There's a top edge, there's a right edge, there's a bottom edge, and there's a left edge. So let's start with top for no particular reason. So this, given a tile, we should basically, so what I'm going to do, because tile is essentially, my tile has a list of strings as its pixel data, right? So what I want to do is, the top edge essentially would just basically be the first row. The top edge is essentially just head. Instead, we will head of pixels, right? Will just be head of pixels, where pixels just extracts the pixel data out of my tile, and then we just head of it. I use the head to get the first first line of the pixels, and that represents a top edge. Let's look at the bottom edge then. Our bottom edge similarly would basically be the last line, the last row of our pixels, right? Exactly. Let's look at the left edge now. Now, as you can see, for the left edge, essentially we basically will have to get the first character of each row, and that would represent our left edge. And so for that, we can simply just map head. On pixels. We can simply just map head on pixels, and that gives us the left edge. And similarly, then the right edge would be map last. Right? Simple enough. Pretty cool, honestly. I'll build a wrapper function which gives me all the edges, and that, given a tile, I don't think we can do. Say we're given a tile. Basically, we have a list of top edge, then right edge, then bottom edge, then the left edge, in sequence, clockwise. Now we have these, and what we want to do basically is apply the tile to each to actually get the edges. This would be right, except Obviously there's repetition here that I want to avoid somehow, and so for that we can basically do a map operation. However, the way map works is we obviously cannot say map tile to these, because what that does is basically it tries to treat tile as a function and then tries to apply this function to this as an argument. But we want to do the reverse, right? We want to do the reverse. We want to apply tile as an argument to the function top edge. And so one neat way to do that in Haskell is use the dollar function, right? So we've been using the dollar function a lot, but let's try and see what it really means. Let's see what, so the dollar function, let's look at the documentation, right? So what it is an application operator, right? And I think the documentation reads pretty good, right? So this operator is redundant, since ordinary application f of x means the same as f dollar x. However, dollar has low right associative binding precedence, which means right associative meaning, if you have a bunch of dollars, you'll start at the right with the functional application and then gradually apply multiple functions. And as you can see in the example here, it clearly states that f dollar g dollar h of x essentially is the same as f of g of h of x. So the dollars are helping us basically get rid of the, it just basically helps us get rid of the brackets, and we can sort of compose the functions in some sort of a linear fashion, right? Rather than this callback approach. Now, and so that is neat in itself. However, in this example is there here itself. So it is also useful in higher order situations such as map $0 to xs or the zip with example, because we can use the dollar function, which basically says, or says that the use tile as an argument is basically, that's what it's saying. And so when we apply the dollar tile to the elements of our list, which is basically a list of functions, so we'll apply dollar tile to top edge, it automatically treats tile as an argument and top edge as a function, and then applies to it. And so that way we basically are able to get the list of edges, or all of the edges, right? I think it's neat. Okay, so now that we have this, now let's think about, okay, how do we determine whether two given tiles are neighbors? Obviously we need to compare the edges. Let's say we have tiles t1 and t2, right? Using list comprehension, let's try to build a list, or rather a pair of edges which are equal, right? Let's try to do that. So let's see, so that will be e1 comma e2, where e1 is going to be coming from edges of t1, right? And e2 is going to be edges of t2, right? So this already so this technically already gives us all the edges. The problem here doesn't like the indentation. Okay, this should be fine. Now, like we said, we want to filter also further, right? We want to filter by matching them. If our matching would be, okay, if e1 is equals to e2, damn, yes, it's adjacent, or even maybe equals to the reverse of it. This would ensure that we will finally come up with a list of all edge pairs that are equal, right? Based on the problem statements, I think we are guaranteed that there's always just be one such pair between any two tiles, Like either it will be either 1 or 0. So basically either our list would have one element or it would be empty. And in fact, all we care about is whether this list is not empty. So I think that's the reason why it's complaining. Let's say ES is this. Oh, okay, that's what's the problem. Let's try the indentation again then, because it's a bit long. Oh, it's happy with this. Nice. This looks nicer. So yeah, let's say we have ES. So now the ES, all we have to make sure is it's not null. The way we can do that is this. Yeah, and this is all we need to do to determine whether two given tiles are neighbors or not. Okay. Now that we have that, I want to build our adjacency matrix, and so this would receive a list of tiles, and then let's say we will be returning a list of tuples, and for each given tile, what is the count of its neighbors. That's what we want to do. That's what I want to do, I think so. Yes. Well, then we could obviously use that to do different kinds of filters, such as filter by where the adjacency, the neighbor count is 2, so meaning those tiles are the corner tiles, right? Let's think about how we can do this. So we have the we know how to determine whether two given tiles are neighbors, and what I essentially want to do is have some kind of a map operation over the list of tiles, ATS, or let's say tiles. I don't know why, but I want to say tiles. I know, forget the H-lint thing for now. So let's say we have tiles. So what we can, in fact, no, let's not ignore it. Let's use it. So what we have to do is we map over the F. Okay, with F we will receive one tile, and so for each tile then we have to compute, okay, how many neighbors it has, right? In fact, this essentially would be a tuple tile and an integer value. Let's say neighbor count, let's say, right? And so let's say this okay, right? That's what we need. Now we need to come up with our algorithm for, okay, what should the neighbor count be? Now for a given tile, obviously we cannot do this without using tile as an input. Okay, so now given one tile, now we have to find out how many neighbors it has. So we can do this in multiple ways. His neighbor, we can map his neighbor tile over all the tiles. Right? We can do this. We'll not map, but we can do filter, and then we can do this. And the only problem with this is we're obviously also including the tile itself, right? Tiles, because tiles includes itself. Let's look at what the other tiles are. The other end we use this. Other tiles, again, other tiles needs tile as an input. We can just use that we can just make use of the this. Not in oh yeah, we just have to okay, we have to import data. This something is there in it's not this. It is this. Is defined in data.oldest. EQ. Oh no, it's just for EQ. Okay, sorry. We just do the default implementation. I don't think yeah. Yeah. The default implementation should be fine. We can further reduce it, but this already or other thing. Obviously we want to export this guy. We'll say Adjacency Matrix. Do we want to expose something else? I think we need it, but we do need. Let me expose this. For now I think we just need this. Okay. Okay, so now we have all our tiles. Let's look at it. Right, we have all our tiles. Let's get the adjacency matrix. Okay, we get the adjacency matrix, which basically is a list of tuples, and then we want to filter. We want to filter and get only the one where the second value is 2, as in only the tiles which have two neighbors. Let's use this. It's not a type thing yet. This would give us a list of all tile tuples where the neighbor count is 2, so basically it'll be all corners, and we can map with FST to get the actual tiles, and then we can use the TileID function to get the actual IDs, and this will finally give me a list of tile IDs which we just have to take a power for. Oh, we do definitely want an int as a return type now. Let's see. Oh, this is this. This filtering. We filter where the second value is equals to 2. That's what we want to do, yes. Apply to too many arguments. We get the adjacency matrix, then we filter this basically gives us the corner type. This gives us the corner type. Right, and then we can use first to actually get the tile, because now we don't really care about, we know all of them have 2 as the neighbor count, so we don't really care about the neighbor count value, we just care about the first value, which is the tile itself. On that, we apply the TileID function to get the actual ID, and then we do our product. Right? That's all we want. What do we do? Okay. That's what I want to do. Okay. Given that, let's look at what this says. So, here is this giant number. Let's look at what's the answer for the test case. Yeah, I think, yeah, good, awesome. Okay, we already have it. Let's also look at what the answer for the actual thing is. Is this 322? Yeah, this looks right. Awesome. So let's look at 0.146, 0.15, roughly about 0.15 seconds. Nice. So we get to look at modules. We get to expand this. Sorry, we get to look at modules. I think our module looks nice. We were able to manage by exposing only 3 functions: the adjacency matrix, tiles, tile IDs. Obviously, I could push this entire thing there if I wanted to, but I don't think that's relevant. Probably going too far. But this was this is definitely the crux of it. Because even for doing the part 2, you do need the adjacency matrix. The difference would be here we only care about the neighbor count, whereas for part 2, we obviously also need to know who the neighbors are. And so typically what you could do for that is, instead of it being an int, you can literally use a list of tiles which would represent the list of the neighbors, right? So, and that way, then finally for the stitching portion, you could use this adjacency matrix in a slightly better way to actually finally compute, right? Because that way we know that given a tile, who are its neighbors? This would be the neighbors. Oops. Hey, I think this looks neat. I like this already so much more than my Ruby solution, which is honestly quite sad and pathetic. I mean, part 1 is easy. Actually, part 1 doesn't look that bad. But I love how this has been broken down, though. That's the beauty of Haskell. That's the beauty of Haskell. Yeah, that's it. All right, guys. Thank you so much. I hope you liked it. Please do share and subscribe, and also comment. I would love to hear your suggestions, your complaints, and your thoughts on the stuff that I'm doing. All right, thank you guys.